In the first part of today's class, we learned about pipeline registers, and now we'll learn about static timing analysis. Okay, so let's first recall what is a setup time and hold time. So when the clock is going high, right? Setup time is the data needs to be stable by a time known as time setup. So the data is not allowed to change during this setup time. Whatever data needs to be placed to the input of the register needs to be placed before time setup. Okay, the setup time, that is like if this is the rising edge of the clock, suppose this is a positive edge in a flip-flop, then the data needs to be stable at this point. Okay, and this difference is given known as setup time. And if the data is going to change and in between here, in somewhere here, then the correct data may not be captured by the flip-flop. And the reason also we have seen when we have learned a transistor level implementation of the flip-flop. There we have seen the reason why it happens. Okay, and also we have learned about T hold. T hold is once the rising edge of the clock has come in, the data needs to remain stable for some time for the data to get captured. Although it is an edge triggered flip-flop, but still there is a requirement for the data needs to be captured by the flip-flop. So you can't have data being changed during this time also. Okay, so these are the two constraints of an flip-flop, timing constraints of any flip-flop. Okay, so there could be a zero hold time and zero setup time systems also, but generally speaking, for every flip-flop there will be something known as setup time and hold time. Okay. Now there is what is a clock skew and jitter. Again we learnt about this. Clock skew and jitter, the only difference you can say is clock skew is because of clocks receiving at various blocks at different times because of the routing issues. It is a something which can be predicted. Okay, clock jitter is because of variance, the deviation in the frequency of the clock, because of temperatures and because of aging issues of the components and all. So this is something which is not predictable. Okay, so there is an uncertainty here. This can be more or less be predicted. Otherwise, functionally they are going to cause the same problems in the circuit. Okay, so clock skew and clock jitter, and clock uncertainty is a sum total of these two. Okay, clock jitter and clock skew. Right. So if you see what are the violations which happens because of clock jitter. So this is an ideal clock which is coming out here. Now in this particular case, if you see the data is changing out here, so there is adequate time available here. Setup time is available here. Okay, now because of clock skew, now this clock is arriving slightly faster out here, right? So in this case, so there is a setup time violation in this case. Okay, because the clock has achieved slightly earlier in this particular flip-flop. Okay, so there is a data setup violation because of the clock jitter in this particular example. Okay. Similarly, here if you see here, the clock is going high here, and the data is pretty stable. So in the first case, when an ideal clock, we are catered for excuse me, for the whole time. But for some reason, if because of the clock jitter, if the clock is delayed in this particular case, then there is a hold time violation. So if you see here, I can say that if the clock is coming early, then there will be an setup time violation. Or if I put the other way around, if the data is coming late, then there is a possibility of setup time violation. Okay, clock early, data late, that will cause setup time violation. Excuse me. Here the clock late or data early will cause data change early will cause an hold time violation. Okay, so these are the things which you need to remember, these two things. Okay. Now what is static time analysis is like there are two problems which can occur. One is known as the hold time violation, and one is known as the setup time violation. So what is the max delay? The data doesn't have enough time to pass from one register to next register before the next clock edge. Okay, that is known as the max delay, because if that happens, then there will be a max delay problem. Similarly, there could be an there could be a min time delay. Min time delay means the data can pass so fast, so that in the next stage the hold time violation would happen. Okay, so these are the two type of problems which can occur in a synchronous system. So you have max delay violations are because of slow data path, including the registers, causing setup time violations, and minimum delay violations are result of short data path, causing data to change before the T hold. So they are known as the hold time violations. So these two types of violations can happen. So when we design a synchronous circuit, we have to compute all these delays to make sure that these kind of violations don't happen. Okay, so excuse me. So setup constraint, if you see here, so there is a flip-flop, there is one more flip-flop out here. So the clock is given here, and in the next clock cycle this data requires to be sampled here, obviously. So that before the next rising edge of the clock, this data requires to move from here to here, and it has to reach here, right? So if you see here, the time period of the clock has to be greater than TCQ. TCQ is what? Time from the clock to Q. So this for the first register, TCQ plus T logic, because there could be a logic in between. So we learnt about pipelining and all, where there are logics in between, right? So this logic block, and then it has to reach before the setup time also. So some setup time requires to be given here. So T has to be greater than these three. Okay, is this aspect clear to all of you? Excuse me. Okay, now if you see here, this is assuming there is no clock jitter. Okay, now if there is an clock jitter, so this time period you have to introduce an clock jitter aspect also here, skew. Okay, if there is a clock skew, even that needs to be included here, right? And also, if you want to give some kind of a margin, okay, in case you want to give some margin, so that to remain on the safe side, so few picosecond margin if you want to give, then you can give this a margin out here in this equation. So now this equation gets modified like this. Okay, then we have something known as setup slack. Okay, data required time, okay, minus data arrival time. Okay, data required time is this, okay, T, and data arrival time is this. So this has to be, if you take the difference, it has to be positive, and if it is positive, then we say there is a positive slack available and there is no timing violation. If it is negative, then that means there is a timing violation. This circuit will not give the correct answers, basic correct output. Basically, the time period, okay, has to ensure that it has to cater for the jitter, it has to cater for all the delays which comes in the path, okay, and also it has to cater for the setup time. Okay, just give me 2 seconds, let me have a glass of water. Yeah, so we were telling, so we need to compute the slack. Okay, the slack has to be always be positive, so that means there is no timing violation. Is it clear to all of you? Yeah, Ravi, Prerna, is it okay? Okay, so there could also be an hold constraint. Okay, hold constraint is once the clock is given here, right? Now we are not talking about the clock and the subsequent clock, we are talking about the same clock period. The clock is given here for the same edge. What happens here? Now, when the clock is rising here, it has to capture the previous data. So, this data requires to be stable for some time. But clock is given here also. Now, this data is coming from here to here. Through this logic, it is coming here, right? So, now if you see here, TCQ plus T logic should be greater than T hold. That means the hold time of this D flip flop, right? And okay, it should be lesser than the time which is taken for this new data to arrive here, right? So TCQ plus T logic has to be greater than T hold. Is this equation clear to all of you? Here we are not talking about two different edges of the clock. For the same edge of the clock, now this is the clock edge is going high out here. Now we are capturing the data. Now this data requires to be stable till for a time T hold, right? So this data requires to be stable out here, right? Now for that to be stable, here also because of the rising edge of the clock, the data is going to get updated, right, till here, right? So so we are not talking about two edges of the clock, of the same edge of the clock. TCQ plus T logic, okay, that has to be greater than T hold, so that we are giving adequate time for this flip flop to capture the data. Then this data can change, and then that data will be captured in the next cycle. Okay, so again, positive slack will be data arrival time minus data required time. Okay, that means the data which has going to arrive here should be later than the hold time here. So you have data arrival time minus data required time. Okay, so that is known as hold slack. So this will be very clear in the few examples which we are going to see today. Okay, here also you can because of the clock skew, you can add an clock skew here, and if you want to have some margin, you can put an margin again. Okay, now see if you here T hold, okay, because of the clock skew, right, this clock can be it can come in advance, right? So you are adding delta skew here, okay, because this clock can come slightly in advance, so you have to cater for that. So you have delta skew out here. A margin is just if you want to be on the safe side, instead of just keeping it both this equal. If you want, say, for unforeseen jitters which are coming in here, if you want to keep a few picoseconds or some percentage margin, so you can add this factor here. No, we can fix in, we can say when we are designing these circuits, we can see to it that there is some margin available. If it is not there, then accordingly the clock needs to be made little slower or faster, whatever it is, right? So that margin we can design. You can have a 10% margin or a 5%, 1% margin. Yeah, correct. So this is to just to cater for. We can't predict. There are certain algorithms which will generally, once you make the chip layout, it will estimate some kind of jitters which is possible based on the routing, right? But then they are all estimates. You need to make some. Yeah, this can be added here or subtracted here, so it doesn't matter. You can do whatever you can do. So that is what we just don't keep too tight. Obviously, we have to we put the margin so as to with age. See, I mean, some of the components they start a little bit a deterioration would happen, right, with constantly running. So just to cater for that, we have some kind of margins. Okay, so unforeseen jitters can be there in the system, so just to cater for that. Okay, so in static circuits and all, those kind of issues generally don't crop up. With aging, you won't have an 0 coming to 1 and all. But at high frequency, these kind of applications, okay, if you're keeping these things too tight, then even a few picoseconds, if it is going to capture the next data, then you find violations and the entire computation going wrong, sir, right? So in all these high speed and dynamic applications, these are all very critical. So, and that is the reason we cater for a little bit of margin out here. Okay, so if you take this example, whatever we discussed will be pretty clear here. Okay, now let's try to compute the setup slack out here, right? If you see here, this is the clock here. Now, when is the clock coming here? You have T period 15. From setup time is from you need to add the clock also, right? So 15 nanosecond. Now we are taking the for setup time. See, the generally for a circuit from here to here in this particular path, okay, maximum delay is 3 nanosecond, and the minimum is 2 nanosecond. I am going to take the maximum, the minimum one, right? Because I am computing the slack now. Setup slack. Setup slack means I am going to find out the worst case scenario, and for the worst case scenario, I will take that the clock is arriving fast and the data is coming late. Okay, clock is coming early in the best case clock and the worst case data. So that will give me the total worst case scenario. Is it okay? Should I am repeating it to find out the worst case setup scenario. I am going to take a fastest clock path and the worst data path. Okay, so the fastest clock path is 50 nanosecond, which is the time period, right? And then you have 2 nanosecond, right, and 5 nanosecond out here, plus 2 nanosecond here, and setup is 4 nanosecond. So I have to put a minus here because that much time also is not available here. So I put a minus 4 nanosecond here. And what about the data path? If you see here, I am taking the worst case. So 2 nanosecond, I am taking this 2 nanosecond. From here to here, it is 11 nanosecond. Then again 2 nanosecond, 9 nanosecond, and 2 nanosecond. So I am taking the worst case data scenario. So I find here now the clock is the next clock is coming at 20 nanosecond, whereas the in the best case scenario, whereas in the worst case scenario the data is reaching at 26 nanosecond. So there is a setup time violation out here. Is it clear to all of you? Okay, now what is setup time? Okay, setup time is when the clock is going high here, this data requires to be stable out here. So we are taking a path out here where the clock is reaching first and the data is reaching clock is reaching here the fastest condition and the worst condition of the data. So in the clock path we are taking all the best case scenarios, and 15 this is fixed clock fixed, but here the best is 2, here the best is 5, here the best is 2, and then setup time is 4. So we are putting a minus out here, 4 nanosecond, whereas in the data path we are taking the worst case 2 nanosecond, here again 2 plus 9 plus another 2. So I have a setup time violation. Similarly, I can do a whole time analysis out here also. Here I am taking the other way around. I am assuming that the data arrival, okay, that is going to be the fastest path. Okay, now I am talking, now there is no clock issue. I am talking about the same edge of the clock. So here it is fastest is 1 nanosecond here, plus this is 9 nanosecond, right? Fastest 11 was the worst, so I am taking 9 out here, then I am taking 1 here, then I am taking 6 here and 1 nanosecond here, right? So this is the fastest the data is coming out here. And what about the clock? Clock I am not taking this 15 nanosecond because in the whole time we are talking about the same clock edge. So I am taking the worst case scenario here. Now 3 here, 9 nanosecond here, 3 here, and then I am holding this, I am putting this in 2 nanosecond also here, right. I can put a minus 2 nanosecond here or plus 2 nanosecond, it's all the same. I'm putting 2 nanosecond, that is the hold time. So here if you see here, there is no hold time violation, because the data is receiving, in the worst case it is reaching at an 18 nano, and this is that 17 nano, right. So this 17 nano includes the 2 nanosecond hold time, right. So if you are not putting 2 out here, then this difference should be more than 2, right. Since we are putting it 2, generally when we talk about slack, we put this 2 and we just have to ensure this is positive or negative. If it is negative, it is a setup time violation. So in the slack equation, you will find that setup time is already included, so that finally we are just seeing whether it is positive or it is negative. Is this clear to all of you? So in your midsem also you can expect some simple problems like this to check whether there is a setup violations or hold time violations. Okay. So let's take one more example. This is an what is the max clock frequency in this particular circuit. So the max, you have an flip flop and then you have an logic, and you are coming back. These kind of circuits you made like counters and things like that in your VLSI design, right? When we make and in the digital design also you might have learnt making sequential detectors, counters and all, where you have a series of flip flops and each of the flip flop input is given through a combinational, like through a combinational thing, right? So here if you see here, the time period, okay, has to be greater than T flip flop, right, plus T combinational plus T setup. Okay, so only then there won't be any setup violation. So this equation needs to be, this condition has to be met, so that there is no setup time. This is the maximum clock frequency you can use, right. So that is there. Now this is one more example out here. Now here it is given the flip flop setup time is 6 nanoseconds and hold time is 2 nanosecond it is given, and the delay from the clock to the Q is given as 10 nanosecond. Now it says calculate the minimum clock period. Okay, if clock period required to handle a circuit by drawing the digital logic for a functional clock, divide by 2 circuit. So you need to make a circuit which is doing divide by 2. So this is a Q bar given to D out here. So this will act like a toggle flip flop, right? So toggle flip flop means every clock, if it is 0 it will become 1, if it is 1 it will become 0, because you are feeding a Q bar to D here. So this is nothing but an T flip flop. How to make a T flip flop using D flip flop? So this is the configuration. So you are giving a clock, so every positive edge of the clock, now the data is toggling from 1 to 0, and so if you see this F out will be, if you see this waveform, it is very clear that the frequency has got divided by 2. So in this particular so this circuit, what is the maximum frequency you can operate? Okay, that is what we need to find out, right? This is a divide by frequency divider, but how it will work without any error for what frequency range, that needs to be found out, right? So you will find a T minimum out here, right, is T setup time, right, T setup time plus an T clock plus delay. That means when the rising edge of the clock, right, the data needs to be stable here. So how is, once the clock has come here, how is the data passing? It has to come from here to here, right, from here to here. So that is 6 nanosecond, right? No, what is the delay? 10 nanosecond. From here to here it is going to take 10 nanosecond, and then this is a short wire which is put here. So we are assuming there will be no delay out here, and then the setup time is 6 nanosecond. So we are adding that 6 nanosecond. So 10 nanosecond plus 6 nanosecond. So T minimum is this. So 1 by T minimum will give you the maximum frequency which is possible for this particular configuration. Is it clear? Right? you have a positive edge of the clock here. So by that, this data needs to be stabilized. So from the clock edge to Q, it is going to take 10 nanosecond. And here there is no combinational block, we have just now put a direct short circuit. So this has become 0 out here, but we need to have a setup time also added to this. So 10 plus 6, this is the 6 is the setup time. So you have 16, so 1 by 6 will give the maximum. Now what about the hold time, right? So once the clock is going high out here, right? So immediately this data is available out here, right? So T hold is it is now it says ki, at least for 2 nanoseconds the data requires to be held here, right? Whereas this delay out here, the new data, okay, once it is sampled the data, the new data which would come here will be after 10 nanosecond, because the time required, the propagation delay here is 10 nanosecond, whereas the data needs to be held only for 2 nanoseconds, because the hold time is given as 2 nanoseconds, whereas the time taken for this new data to get refreshed here is 10 nanoseconds. So there is no hold time violation in this case. Okay. So this circuit can perfectly work fine. So work at this particular frequency in this configuration. So these are the kind of analysis which you need to do, right? Okay. So that's all for today. So all the best. So that's all for today.